When you train a machine learning model, you've probably set an optimizer to something like Adam and just moved on. But what is that optimizer actually doing? How does a model learn to get better? Well, by the end of this, you'll get the core intuition behind the algorithms that make it all happen.
So let's start with that big question. How does a model systematically improve itself? It's not magic, it's actually a pretty clever process, one that we can visualize with a simple analogy.
Imagine you're standing blindfolded in the middle of a huge, hilly terrain. Your only goal is to find the absolute lowest point in the entire landscape. That's it. This is the exact challenge a machine learning model faces when it's training.
This hilly terrain has a name. We call it the loss landscape. Every single spot in this landscape represents a different version of our model, and the altitude, how high up you are, tells you how wrong the model's predictions are.
The formal term for that wrongness score is the loss function. The whole point of training is to find the coordinates in this landscape that give us the lowest possible loss. So, the real question is, how do we navigate this landscape when we're blindfolded?
Well, the most basic strategy is an algorithm called stochastic gradient descent, or SGD. It's the simplest tool our blindfolded explorer has. The idea behind SGD is super simple. You can't see the whole landscape, right? So you just feel the slope right where you're standing, using just a single piece of data, and take one step in the steepest downhill direction. Then you just repeat that over and over again.
But there's a pretty big catch. Because each step is based on just one data point, the direction is really noisy. Instead of a smooth, confident walk to the bottom, the path is erratic. It zigzags all over the place.
And you can really see the problem here. On the left, that's the ideal path, a nice smooth trip down the valley. But on the right, that's SGD. It's wasting a ton of energy bouncing between the steep walls of this ravine, making really slow progress down toward the minimum.
So, to navigate these tricky ravines better, our explorer needs some upgrades. And two key ideas came along to solve SGD's problems: momentum and RMS prop. Think of momentum like giving our explorer a skateboard. Instead of just taking one jerky step at a time, you start building up velocity from your past steps. This helps you glide right over little bumps. And in those ravines, the side-to-side movements start to cancel each other out, but the momentum in the true downhill direction just keeps getting stronger.
Now, RMS prop is a different kind of upgrade. Think of it like a pair of high-tech adaptive shoes. These shoes sense how steep the ground is. On the really steep walls of the ravine, they take tiny, careful steps to avoid overshooting. But on the flatter ground at the bottom, they take much bigger strides to cover ground faster. It adapts the step size for each direction.
So we've got a skateboard to keep our direction steady and adaptive shoes to adjust our step size. You can probably guess the next question. What happens if we combine them? Well, that's exactly what the Adam optimizer does.
Adam stands for Adaptive Moment Estimation, and it's really the best of both worlds. It takes the direction smoothing idea from momentum and combines it with the adaptive step size from RMS prop.
So on a slightly more technical level, Adam tracks two things. The first moment, which is just the average direction, just like momentum, and the second moment, which is all about the steepness, like RMS prop. It also has a clever little correction to make it more stable right at the start of training.
And the results, well, they usually speak for themselves. In this simple comparison, you can see that Adam doesn't just get to a lower final error. It gets there way, way faster than the others. The difference is pretty dramatic.
Okay, so why does this matter in the real world? Because the optimizer you choose has a huge impact on how long it takes to train your model and ultimately how good it will be.
For all these reasons, Adam has become the standard, default choice for deep learning. It's fast, it's efficient, and it's generally less fussy about the initial settings you give it. That's why it's the go-to optimizer in frameworks like PyTorch and TensorFlow. It just works well most of the time.
So next time you hear about a massive new language model or some cutting-edge generative AI system, you can be pretty sure that Adam, or a very similar algorithm, is the engine driving the training process behind the scenes.
So, to put it in one sentence, Adam finds the best solution faster by intelligently combining momentum with adaptive step sizes.
This all leads to one last important question. If it's so good, is there ever a reason not to use Adam?
And surprisingly, the answer is yes. While Adam is fast, some research suggests it can find sharp solutions in the lost landscape. Sometimes a simpler optimizer, like SGD, finds a flatter valley, which can actually lead to a model that performs better on new data. So the key takeaway is this. Adam is an amazing default, but the quest for the perfect optimizer is far from over.